Hi everyone, I hope you all are doing well this fine night. And as some of you may remember, all my previous presentations have revolved around cybersecurity and encryptions. Well, tonight we're going to be going over how to create and implement an encryption. Sounds neat, right? So let's do a general overview of what we're going to be going over today. Before you can start creating your encryption, you have to ask yourself, what am I looking for? Each encryption style is unique. Each one caters to a specific task. Before you can begin coding anything, you must find out what your overall objective will be. After that, we will discuss the programming languages you can code your encryption algorithm in, and why choosing some languages for some algorithms may be more efficient or can be more secure. From there, we'll get to the fun part and do a live demonstration. We'll go step by step, incorporating our algorithm into an encryption to develop our keys. After we have successfully created our encryption algorithm, we will discuss when, where, and how to implement it. And finally, we will wrap everything up with a simple conclusion. As you may recall, there's a significant difference between symmetric and asymmetric encryptions. Those who don't remember, here's a brief overview. Symmetric encryptions use only one key, and while this allows the encryption to execute swiftly, it comes at the cost of some security. You will always have to share your private key with the opposite party. Yet, because of its speed, it's commonly used for e-commerce transactions. And if that doesn't seem like something you'd want to do, that's where asymmetric encryptions come in. Asymmetric encryptions use two keys, a public and a private key, and because of the encryption and decryption by two separate keys, and the process of comparing them makes executing the encryption a tad bit slower. Yet, it allows you to share the data without sharing the same encryption key. In fact, most websites use asymmetric encryptions. This is where TLS, Transport Layer Security, and SSL, Secure Sockets Layer protocols factor in. This is what makes HTTPS on sites possible. Choosing which encryption method to use solely depends on what you'd like to achieve. In my demonstration coming up, we will be focusing on symmetric encryptions, more specifically block cipher algorithms. The reasoning behind choosing to implement a symmetric encryption tonight is due to the fact they're the most popular and easier to implement compared to asymmetric encryptions. We will be dissecting the AES Advanced Encryption Standard Symmetric algorithm and implementing it into our own encryption. Continuing on, so how exactly do you program an encryption? What do you use? Are there specific tools to have? Programming the actual encryption can happen in practically almost any programming language you'd like. IDEs are not necessarily needed, yet they can help you with debugging and formatting your code in a proper structure. To convert the encryption algorithm, you just have to implement the pseudocode onto actual code. Selecting your language can make a difference in some cases, yet all in all, as long as you have a general idea of what you'd like to do, a majority of higher level languages can execute most encryption methods. Personally, I love Python. Its simplicity and ease of use has always catered to my needs whenever a simple project or program is needed. Our demonstrations in the coming slides will be utilizing Python programming to encrypt and decrypt a user's message. On the other hand, if Python is not something you're too familiar with and like to base yourself off object-oriented programming, then a C++ encryption method can better suit you. Keep in mind both Python and C++ have an extensive amount of resources and IDEs available to anyone on the web. Regardless, here's a straightforward simplified demonstration of a C++ program that encrypts and decrypts a plain text string using the RSA algorithm. The RSA algorithm is an asymmetric algorithm that uses both a public and a private key. In this situation, the public key will be used for encryption, and the private key is used only to decrypt the encrypted message. This encryption method undergoes a series of steps to create the keys, encrypt the message, and lastly decrypt the message itself. In creating the keys, the user will select two large prime numbers, an x and a y. From there, the algorithm will compute n equals x times y, where n is the modulus of both the private and the public key. Next up is calculating Euler's-Titoian's function, which results in 5n. From there, choose an integer e such that e is coprime to the 5n and yields 1 less than e less than 5n. E will become the public key exponent used for the encryption. Finally, choose an integer d so that d times e mod 5n equals 1, which will be used to generate the private key function. Onwards to encrypting the actual message, the public key is both the function of e and n integers. The ciphertext is then calculated by c equals m to the power of n mod n, where m is the plaintext message and c is the ciphertext. Once we have our encrypted message, we need to know how to decrypt it back to plaintext. Using the calculations from earlier, we understand that the private key is the function of both d and n. This time, to decrypt the ciphertext, the equation is followed by m equals c to the power of d mod n. And that's it. That's the entirety of the RSA algorithm. Seems simple enough with all the resources online. You can get links to Python, C++, and even assembly language source codes. And although assembly language may get too complex, it allows you to communicate with your machine on a deeper level. The programmer can implement code in such a way where it can be more memory efficient and execute faster than a higher level language. I can include a very detailed video implementing an RSA encryption in assembly language in the description below. Yet, implementing an algorithm is not restricted to only these three languages. Java, JavaScript, C, and Swift are just a few more examples of languages you can use yourself to implement said algorithms.
Now that you have a general idea of which programming language to use, it's up to you to decide which algorithm to implement your encryption in. If you're looking for speed, symmetric algorithms are what you need. Yet, depending on your situation, a symmetric stream cipher could be more efficient than a symmetric block cipher algorithm. Stream ciphers are good for fast implementations with low resource consumption. These two features help the defender implement resistance strategies in devices that may not have the resources for a block cipher implementation. Stream ciphers are also useful for encrypting wireless signals, which more naturally fit a streaming model than transmitting data in larger fixed-size chunks. For example, the A51 stream cipher is used in GSM phones, and the RC4 stream cipher has been used in the security system for wireless local area networks, also known as WLANs. But essentially, there are three modes of data that need to be protected: data in motion, data at rest, and data being processed. Stream ciphers usually protect data in motion, while block ciphers are commonly used to protect data at rest, such as on file systems or specific size database fields, and can be more efficient when the size of the data is actually known. Block ciphers, if used properly, are an effective method for resisting adversarial attempts to read data. The foremost example of a modern block cipher is the AES encryption. Certified in 2001, AES has been something of a de facto standard cryptographic algorithm. A block cipher maps each possible input block of plaintext to an output block of ciphertext. For a cipher with 64-bit inputs and outputs, to write down this complete mapping would take about 2 to the 69 bits, or about 74 exabytes of memory. This becomes too much, and to efficiently use large enough input blocks without using an infeasible amount of memory, ciphers are used. A well-designed cipher will map an input value to an output value using the key in such a way that the mapping appears random unless one knows the key. Modern block ciphers tend to have block sizes of 128 bits or larger. Because if the block size is too small, then a problem arises. The adversary can enumerate all the possible options and thus undermine the actual algorithm. On the other hand, if you're looking for reliability and security, asymmetric encryptions could be your answer. Their use of two keys provide an enhanced form of safety. It ensures those who have a key can't misuse them, and it allows for the sending party and the receiving party to communicate with one another even if their lines of communication are being observed by a third party. And because of the multiple key nature, it allows communicating parties to share their public keys and using complex math, encrypt data such that an eavesdropper cannot decipher the message. Message authentication based on asymmetric keys is also possible. This is called the signature scheme. A signature scheme consists of three operations: key generate, sign, and verify. Signature schemes were invented to facilitate authentication. Asymmetric encryptions, on the other hand, are far slower compared to their counterpart, symmetric encryptions. In fact, they can be up to 100 to 1,000 times slower. The most well-known symmetric encryptions include AES, Triple DES, IDEA, Blowfish, and RC4 through 6. The most well-known asymmetric encryption algorithms include Diffie-Hellman, RSA, ECC, Elgamal, and DSA. There are even far more encryption algorithms to choose from, but the possibilities are endless. You can even design and create your own using the language of your choice. Choosing the right algorithm is important because vulnerabilities are discovered over time. Advances in computing processing power may mean that a brute force attack is no longer a time-consuming task. Such examples include the original DES algorithm, which was the national standard for more than 20 years until the late 1990s. During that time, computing power had advanced to such a point that it was possible to brute force crack a DES key in less than 24 hours. In the early 2000s, the AES encryption was then published as a replacement for DES. An AES with 256-bit key size has a potential of 115 quadrivigintillion possible keys, or 115 with 78 digits following it. There is presently no known practical attack that could brute force an AES 256-bit key. But you should therefore regularly assess whether your encryption methods remains appropriate. Also, rather than developing a custom algorithm, it is recommended that you use a trusted and verified algorithm. This can provide an assurance of suitability and also permit you to demonstrate a level of compliance with legal obligations. However, it is still important to regularly review the algorithms you choose, due to the nature of technical development over time. Now, we have our language, we have our encryption, so what's next? An IDE. An IDE provides ease when it comes to programming. It allows the programmer to increase productivity by common activities of writing software into a single application, editing source code, building executables, and debugging. Well, you guys already knew that, or at least I'm sure. You're almost software engineers. Nonetheless, since we're focusing on Python for our demonstration, I suggest using Microsoft Visual Studio Code as a preferred IDE for programming the AES encryption. Now here comes the fun part, our demonstration. So let's pull up Visual Studio Code and, well, before we can demonstrate the actual AES encryption, we have to know what's going on. So to describe everything, under this method of encryption, the first thing that happens here, plain text, is separated into blocks. The block size of the AES is 128 bits, so it separates the data into a 4x4 column of 16 bytes. Well, essentially, once we have our 4x4 column with the 16 bytes, we then have to perform a key expansion. Key expansion involves taking the initial key and using it to come up with a series of other keys for each round of the encryption process. These new 128-bit round keys are derived with Rehandel's key schedule, which is essentially a simple and fast way to produce new key ciphers. So following that comes the actual encryption process. And given our plaintext block, we use 4 different transformations in the initial round, the 9 main rounds following that, and then our final round at the end. So as you can see, this is a general overview of how the actual encryption process works. In the first round, our initial key is added to the block of our message, and this is done with the XOR cipher, which is an additive encryption algorithm. And then following that is our substitute byte step. In this step, each byte is substituted according to a predetermined table. And as you can see, our 19 is substituted to a D4, and then it just continues on for each of the bytes inside the block. And following that is our shift rows step. Shift rows is just a straightforward name. This step essentially is what you would expect. The second row is moved 1 space to the left, and the third row is moved 2 spaces to the left, and the fourth row is moved 3 spaces to the left. So the third transformation in our encryption process is the mixed columns transformation. And essentially what happens is each number, each column are modulo multiplied in Rehandel's Galois field by a given matrix, and that results in the following numbers. The mixed column step along with the shift row step is the primary source of diffusion in Rehandel. So following our mixed columns transformations, we once again have the add round key transformations. So the round keys we made at the start using our initial key and our Rehandel's key schedule, well, this is where we start to use them again. We take the result of our mixed columns and add the first round key that we derived, and we get that output. These transformations are applied to the state for 9 rounds. The final round does not include the mixed columns transformations though. So now that we've talked about each of the transformations, I'm going to let the animation continue going on in the background while I'm just talking. So if you thought that was it, we're not even close. After the last round key was added, it goes back to the byte substitution stage, where each value is changed according to a predetermined table. Once that's done, it's back to shift rows and moving each row to the left by 1, 2, or 3 spaces. Then it goes through the mixed columns equations again. After that, another round key is added. And it doesn't stop there. At the start, it was mentioned that the AES keys we will be using was 128 bits, but it can also be 192 or 256 bits. When a 128-bit key is used, there are 9 of these rounds. When a 192-bit key is used, there are 11. When a 256-bit key is used, there are 13. So the data goes through the byte substitution, shift rows, mixed columns, and round keys steps up to 13 times each, being altered at every stage. After these 9, 11, or 13 rounds, there is an additional round in which the data is only processed by the byte substitution, shift rows, and add round key steps, but not the mixed column step. The mixed column step is taken out because at this stage it would just be eating up processing power without altering the data, which would make the encryption method less efficient. So just to make things clear, the entire AES encryption process goes key expansion, add round key, byte substitution, shift rows, mixed columns, add round key, and that could go up to 9 to 11 or 13 times depending on how big the key size is. And then the final round goes byte substitution, shift rows, add round key. And once the data has gone through this complex process, it seems like a completely random string of characters, but it is actually the result of many different mathematical operations being applied to the same key over and over again. So what's the point of each of these steps? A lot of things happen when our data is encrypted, and it's important to understand why. Key expansion is a critical step because it gives us our keys for the later rounds. Otherwise, the same key would be added in each round, which would make AES easier to crack. In the first round, the initial key is added in order to begin the alteration of the plaintext. The byte substitution step, where each of the data points is changed according to a predetermined table, also performs an essential role. It alters the data in a nonlinear way in order to apply confusion to the information. Confusion is a process that helps to hide the relationship between the encrypted data and the original message. Shift rows is also critical. Performing what is known as diffusion in cryptography, diffusion essentially means to transpose the data to add complication. By shifting the rows, the data is moved from its original position, further helping to obscure it. Mixed columns acts in a similar way, altering the data vertically rather than horizontally. At the end of each round, a new round key that was derived from the initial key is added, and this adds greater confusion to the data, enhancing our security. So decrypting the AES encryption is rather simple if you understand everything about the encryption process that was just explained. To go from the ciphertext back to the plaintext of the original message, everything is just done in reverse. So inverse the add round key, inverse shift rows, inverse byte substitution, and we do this 9, 11, or 13 times depending on how large our key size is. Because AES performs these steps a number of times, AES itself still remains secure to this day. It's an excellent standard for securing our electronic communication and can be applied in many situations where sensitive information needs to be protected. Judging by the current level of technology and attack techniques, you should feel still confident using it well into the foreseeable future, and that is why we're about to implement it right now. We have Visual Studio Code all open, and we created our advanced encryption.py program. We can start programming our simple advanced encryption 256-bit counter non-authenticated encryption. So we first have to install the correct libraries that we will be using for this program. So we could do pip install PyAES and pbkdf2. I'll describe what they are while it's installing. So PyAES implements the AES symmetric key encryption algorithm. So we don't have to actually program all that. It's already all set online for us. So that's just a tremendous amount of help. pbkdf2 is a password to key derivation algorithm, so that will also help us when we're creating our key. So beginning everything off, we have to import the correct library. So the ones we just installed, pbkdf2, binary ASCII, OS, and secrets. So these three should already come with Visual Studio Code, so no need to install those, but if you do need to, you could just do pip install and whatever binary ASCII, OS, or secrets, whichever ones you need. So we first create our password. You gotta make it a little complex so it's not easy to crack, or easy to guess. So we could just do secret code with letters and numbers and an asterisk. Just like that. And that's our password. And then we're gonna need to do a password salt What password salt is just a sequence of bits. So we're right now going to be passing in random 16-bit sequence. And then now we can develop our key using the PBKDF2 algorithm. We pass in our password and our password salt and read 32. Alright, so now we get to print it out what our key is. AES encryption key, and then we do binary ASCII, hexlify, and we pass in our key. And let's see what that outputs. Alright, yeah, so here's our advanced encryption standard key right there. Look at that. And every time we do run it, it should be different because we are using urandom, so we're always going to get a random sequence a bit. See right there? It's random again. Perfect. This code derives a 256-bit key using the PBKDF2 key derivation algorithm from our password secret code. The derived key consists of 64 hex digits, or 32 bytes, and it represents a 256-bit integer number. And as you saw, every time we did run the code, it was different. Like, we could try it again. And this is because we used a random salt. If we did use the same salt, the same key will be derived every time you run. We've written out the code to actually generate our AES key. We now have to generate a random 256-bit initial vector for the AES counter block mode. So what we can do is just this, where our initial vector uses the secrets library, and of course it generates a random 256-bit number. Then we can perform the actual AES 256-bit counter encryption. So getting some code from online. As you can see, this is our plain text, and our plain text can be any string. It can even be a file that we read in and we pass into this variable. And then from there we use the AES variable, and this uses the PyAES library. And we pass in our key and our initial vector. And then for our ciphertext variable, we pass in our plain text, and that encrypts our plain text and puts it all in our ciphertext, and then we print out our ciphertext at the end, as I'll show you. So for this run, this will be our key, and using this key, this is our encrypted message. So if anyone intercepts this message, this is what they'll be seeing instead of text for encryption. Of course, we can change that up. So let's say we could put AES encryption example. And this time, because we're running it again, it will generate a random key, another random key, and our encryption will be different. As you can see, this time it's even longer. So yeah. Code to encrypt our plaintext. Let's talk about what's actually going on. So if we revert our code back to, if we revert our plaintext string back to text for encryption, we can see that our ciphertext will actually be consisting of 38 hexadecimal digits. And this is due to the size of our input data, which is text for encryption. Note that after the AES CTR encryption, the initial vector, IV, should be stored along with the ciphertext, because without it, decryption will be impossible. The initial vector should be randomly generated for each AES encryption, not hard-coded, and this is due to the fact that it increases security. Also, if you encrypt the same plaintext with the same encryption key several times, the output will be different every time, and this is due to the randomness of the initial vector. This is intended behavior, and it increases security, especially against dictionary attacks. Guys, so now that we figured out how to encrypt our plaintext message, let's see how we can decrypt our ciphertext using the AES CTR 256-bit algorithm. So essentially the input will be consisting of the ciphertext, encryption key, and the initial vector for the CTR counter. And the output will be our original plaintext. And using the code we got from online, the code is actually pretty simple. Here you go. So we decrypt the ciphertext with a given key, and using our PyAES library, we can decrypt it using our ciphertext. And if we run it once, we get the AES encryption key, our encrypted message, And our text for encryption, decrypted ciphertext. How cool is that? And if we change our plain text to, I believe, AES encryption example, once again we get a different key, different encryption ciphertext, and we get our same decrypted plain text. So yeah, let's dissect what's actually going on in this decryption process. As you can tell, this AES variable is actually being initialized again, and this is because the CTR cipher block mode algorithm keeps an internal state that changes over time. Also, this entire code block cannot detect the wrong key, the wrong ciphertext, or wrong initial vector. If you use an incorrect key to try and decrypt the ciphertext, you'll get a wrong unreadable text. And I could demonstrate this in the coming code below. So as you can see, we develop a new randomly generated key, and we're going to try to decrypt our plain text with this. So here's our original AES encryption key. Up next is our ciphertext that we used the key with, and then using the correct key we deciphered it back to our plain text, and using the incorrect key, this is what we get, a random path to nothing, essentially. And all in all, this is the AES 256-bit CTR encryption algorithm. And as you can see, it's fairly simple, and thanks to these libraries provided by these guys, that it makes our lives easier. People have already done everything, and most of the source code is already online. I will include some links down below that you can check out, and they have more AES variations, essentially. After creating our encryption algorithm, let's go over situations when we would actually use encryptions. So, protecting sensitive data in case your laptop is stolen. If your laptop is stolen, encryption will prevent a thief from booting it up and looking through your sensitive data for financial information and other sensitive things. Realistically though, your average laptop thief probably just wants the hardware and will probably wipe the drive quickly. But if you do have sensitive documents on your computer, encryption makes the most practical sense. Storing or sending sensitive data online. When storing something particularly sensitive, perhaps archives tax documents that contain personal data, like your social security number, in online storage, or emailing it to someone, you may want to use encryption then as well. Or for the business case, for businesses there may be various commercial guidelines or rules requiring the use of encryption. These are intended to prevent the terrible stories we hear about business laptops being stolen out of cars, and those laptops having massive databases containing millions of customer credit card numbers on them. So up next, where do we implement encryptions? You can practically implement encryptions in almost anything that stores and holds data. The list can go from transferring data by CD, DVD, USB, email, online websites, fax, to databases, photography and video equipment, audio recordings, and the list can just go on and on. Encryptions are practically prevalent in almost everything we use in our everyday lives. They have become basically a necessity when it comes to technology and our personal data. How we implement our encryption is all dependent on choosing the right algorithm, key size, software/IDE, and how we plan on keeping our actual key secure. As we demonstrated earlier, when we chose the AES algorithm, a 256-bit key size, and we used Microsoft Visual Studio Code as our IDE, and we can secure our key using pen and paper, a USB device, or practically anything we know we can keep safe ourselves. And that's the overall gist of how to create and implement your very own encryption to protect your data. Thank you everyone for taking the time to watch this video, and I hope you all have a wonderful night. If you'd love to contact me more, here's my LinkedIn and my email. Looking forward to hearing from you guys. Thank you, and good night.